So we've described the process of biological denitrification and compared it with the process of biological nitrification. Now we're going to define the requirements that we need to impose in an activated sludge reactor in order to effect biological denitrification. In other words, establish denitrification in our system. So the first thing we require is the presence and the input of nitrate. So if we have an anoxic reactor in our activated sludge system, somehow nitrate needs to be introduced to that reactor in order to do biological denitrification. The second thing we have to ensure is that in this biological reaction, or in this anoxic reactor, there must be an absence of dissolved oxygen. That is what we define anoxic, is the absence of dissolved oxygen. Now that is more than just measuring a zero dissolved oxygen concentration in the reactor. There also should be no input of dissolved oxygen into the anoxic reactor, because any oxygen that I put into the anoxic reactor is going to be consumed preferentially by the ordinary heterotrophic organisms before they will use nitrate. The reason why the ordinary heterotrophic organisms prefer to use oxygen to nitrate is because they can generate more catabolic energy per electron transferred with dissolved oxygen than they can with nitrate. And so they will always use the oxygen first if oxygen is present. So we need to ensure that in our anoxic reactor there is as little possible input of dissolved oxygen in the reactor. We then need this facultative heterotrophic biomass, and also we need a suitable electron donor to perform this biological denitrification reactor, and in many instances these would be organics. I'm going to describe each of these requirements in a little bit more detail. The source of the nitrate, of course, is our nitrification process, which we've discussed in detail. Therefore, nitrification is a prerequisite for denitrification. If we don't nitrify, we cannot denitrify, and we will not be able to remove nitrogen. The system sludge age, therefore, must be longer than the minimum sludge age for nitrification, which we defined as R subscript SM, minimum sludge age for nitrification. Or alternatively, if a certain sludge age is already imposed on the system, we must ensure that this anoxic zone does not exceed the maximum unaerated sludge mass fraction that would prevent the nitrifiers from growing in the activated sludge reactor. And we discussed this maximum unaerated sludge mass fraction in detail in the nitrification section, but it's worth repeating because it is the most important decision that is made in the design of a biological nitrogen removal system. And so we established from our nitrification kinetics that the maximum unaerated sludge mass fraction that I'm allowed to impose on a activated sludge reactor is 1 minus the factor of safety of nitrification, which is essentially a reduction factor on the maximum specific growth rate of nitrifiers, the endogenous respiration rate plus the inverse of the sludge age. And this equation here is plotted as lines in this graph. So, for example, a maximum specific growth rate of 0.4 per day for the nitrifiers, if the sludge age is 8 days, the whole system has to be aerobic because the maximum unaerated sludge mass fraction that I'm allowed is 0. Then as the sludge age begins to increase, so I'm allowed to include a reactor that has a certain unaerated mass fraction. And when the sludge age is 10 days, then 20% of the mass of sludge in the system is allowed to be under non-aerated conditions and still ensure nitrification. And so here you can see that as I increase the sludge age, now if it's 20 days, I can have as much as 50% of the mass of sludge in the reactor in a non-aerated condition. Of course, the larger the unaerated mass fraction in the system, the more nitrate I can denitrify. So already within the choice of sludge age, unaerated sludge mass fraction, dictated by the maximum specific growth rate that I have for the particular wastewater that I'm dealing with, I have to already know what is my effluent nitrate concentration going to have to be. Does it have to be extremely low? If it is, you can see I will be forced to choose long sludge ages because I will need large unaerated sludge mass fractions in the system. And it is for this reason that I say that the choice of sludge age, unaerated mass fraction, is the most important decision that you make, because already in the back of your mind you will have, what effluent nitrate concentration do I require? If you do not require a very low effluent nitrate concentration, you can choose small anoxic mass fraction, short sludge age. So this decision that we make here is the most important in design, and I emphasized that yesterday in the discussion on nitrification. I emphasize it here again in our lecture on denitrification. Dissolved oxygen is inhibitory on the biological denitrification process. And if the dissolved oxygen concentration is 0 in the activated sludge reactor, then denitrification will proceed at 100%. If the dissolved oxygen concentration is 0.5 milligrams per liter, there have been instances where the denitrification is actually 10% of what it would have been if the dissolved oxygen concentration is 0. However, I want to stress that even if the dissolved oxygen concentration is 0 in the reactor, the DO entering the reactor will be used first, and therefore we must avoid dissolved oxygen ingress into the anoxic reactor. And in some instances, the anoxic reactor would be covered so that it has no open headspace to the atmosphere, because the reactor needs to be mixed, and in the mixing action we create vortices and free surface renewal, and so dissolved oxygen from the atmosphere can enter the anoxic reactor. In some instances, I've seen also that coarse bubble aeration is used to mix anoxic reactors. That would not be as good as using a motor and a stirrer to mix the anoxic reactor contents, because coarse bubble aeration will introduce oxygen into the biological reactor. Sources of dissolved oxygen that we have on real systems, high concentrations in the recycles from the aerobic zone. So control of dissolved oxygen becomes a very important issue in the biological reactor. We want the oxygen concentration high enough not to slow down the nitrification reaction, but we also don't want it too high to slow down the biological reaction of denitrification via the recycle. If the dissolved oxygen is too low, we will get anoxic pockets in the aerobic reactor. And then, even though I think, because my anoxic reactor is, say, 20% of the volume of the entire system, I in fact have a 20% anoxic mass fraction, if the dissolved oxygen concentration in the aerobic reactor is very low, I create unintentional anoxic pockets in the aerobic reactor, and then my anoxic mass fraction is in fact larger than I think it is, and I may not nitrify as well as I think I should be. Then, of course, there is the problem of entrainment of air and oxygen at the liquid interface. If I have high mixing energies in the anoxic reactor, and then we have entrainment in recycle flows where there may be screw pumps that return sludge to anoxic reactor, or cascades or hydraulic jumps in channels that carry mixed liquor back to the anoxic reactor. All these are aeration devices in a way and should be avoided. Thirdly, we require a facultative biomass. Now, the ability to denitrify amongst ordinary heterotrophic organisms is widespread. And in activated sludge systems, significant number of these ordinary heterotrophic organisms are facultative and therefore have the ability to both denitrify and use dissolved oxygen as terminal electron acceptor. In fact, it's interesting that there's very little difference in the biological populations when you do fish analyses and organism identification. There's very little difference in the bacterial populations in a fully aerated system or in an anoxic aerobic system in which biological denitrification takes place. Aerobic activated sludge requires a few days to acclimatize to denitrification conditions to denitrify at full capacity of the biomass. And then finally, there is the fourth requirement that we need to do biological denitrification, and that is the electron donor. Now, generally, of course, organics are electron donors, and the sources of these organics are threefold. First of all, we have internal electron donors. These are the electron donors that we have present in the influent wastewater. Secondly, we would have what are called self-generated, by the biomass, electron donors. And these would be the electron donors that are generated via the endogenous respiration process, or you may remember we discussed this death regeneration process. So it's the organics that are generated through the death and lysis of live organism mass, and then that these biodegradable organics get reused to grow new organism mass. But it's nevertheless self-generated because it's from the biomass itself. And then thirdly, we have external electron donors, and these are the ones that would be dosed to the activated sludge system, for example, methanol or any other waste organics that might be available locally with proximity to the activated sludge system. Now, from our perspective, electron donors number one, that is the internal ones, those present in the influent wastewater, and number two, which are the self-generated ones, are of most interest to us in wastewater treatment because we're really using the organics that we have available and we're not spending money on buying others. However, the third one, that's the external electron donors, may have to be used if we need to get very low effluent nitrate concentrations, because there are limits to how much nitrogen we can remove with the internal and self-generated electron donors. Different wastewater or activated sludge configurations have been developed, and these have been categorized and named depending on the type of electron donor that is utilized in that kind of denitrifying environment. And the first one is a system which has been named after Wurman, who was at the Swiss Federal Institute of Technology in the early 60s, and this system is called the Wurman system, as it essentially uses the self-generated electron donor. Then there is the modified Lutsak-Ettinger system, or abbreviated MLE. It uses the internal electron donors. That's therefore the electron donors in the influent wastewater. And finally, there's the four-stage Baden-Foe, which is the internal and self-generated electron donors, but sometimes methanol is dosed into the secondary anoxic reactor if low effluent nitrate concentrations are required. I'm going to briefly describe the configuration of each of these systems. First of all, the Wurman system. This form of denitrification is called post-denitrification because the denitrification takes place in the anoxic reactor, which follows the aerobic reactor. Now, in this particular system, all the influent biodegradable organics will be utilized in the growth process aerobically. And therefore, there will be very little influent biodegradable organics left over moving across to the anoxic reactor. And therefore, the only electron donor available for the denitrification is the self-generated electron donor through the endogenous process. Now, the endogenous process is very slow, as we discussed, and so the rate of denitrification in this secondary anoxic reactor, as it's also called, is very slow, and therefore we need a large unrated mass fraction in order to get a high nitrate removal. And so in order to derive a greater benefit from the secondary anoxic reactor, often methanol is dosed into the secondary anoxic reactor to improve the denitrification. Next, we have the modified Luksak-Ettinger system. This is called pre-denitrification because the anoxic reactor comes before the aerobic reactor. Now, we have all the influent biodegradable organics available for denitrification. However, the first process of nitrogen removal happens after the nitrogen removal process, the denitrification reactor. So in order to introduce nitrate and mix it with the biodegradable organics of the influent, we have to have these recycles which introduce nitrate into the anoxic reactor. And we need to make sure that sufficient nitrate is recycled to the anoxic reactor in order to remove as much nitrate as possible. So here we gain in the system because we are using the influent wastewater organics for denitrification, but in a sense we lose because we can never get complete denitrification because there will always be some nitrate that escapes with the effluent that we cannot denitrify because it's impossible to recycle all the mixed liquor to the front in the primary anoxic reactor. Now, in order to get a high nitrogen removal, we need to have high recycles. And on this graph here is shown the percentage nitrogen removal that I would achieve in the anoxic reactor for the A recycle ratio. And you can see that if the A recycle ratio increases from, let's say, 6 times the influent flow to 8 times the influent flow, and this anoxic reactor denitrified all the nitrate returned to it, I improve my nitrogen removal only from about 87% to 90%. So I gain very little additional nitrogen removal for a very large increase in pumping flow cost. And it's this reason that a practical maximum A recycle ratio is established on the system at around 5 to 6 times the influent flow, because the gain after higher recycle ratios is not worth the pumping costs. The third configuration for biological denitrification is called the 4-stage Barden-Foe process, and it is a combination of the primary anoxic reactor and secondary anoxic reactor. Here, in the primary anoxic reactor, we utilize the influent biodegradable organics to drive the biological denitrification process and get substantial nitrate removal in the primary anoxic reactor, and any remaining nitrate that passes through to the effluent would be denitrified in the secondary anoxic reactor using the self-generated electron donors. However, because the denitrification rate by the self-generated electron donors is relatively small, this process is sometimes used and methanol is dosed into the anoxic reactor to keep the secondary anoxic reactor small in relation to the primary anoxic reactor, because methanol has a fast denitrification rate. It in fact works as a readily biodegradable organic material. So complete denitrification in the 4-state Barden-Foe is possible, but the influent TK-NCD ratio has to be low, because if I have too much nitrate generated via the nitrification process in the aerobic reactor, I do not have enough internal electron donors available in the primary anoxic reactor and self-generated electron donors in the secondary anoxic reactor to denitrify all the nitrate.